Today we are discussing the soil classification system, which is universally accepted by all the geotechnical or civil engineers. In previous classes we discussed the index properties of soil, and we have also seen the index properties are those properties of a soil which gives a basis, and on the basis of which we classify a soil. So accordingly we have seen soil grain properties and soil aggregate properties. So soil grain properties means size, particle shape, and particle specific gravity, so on and so forth. And also we have seen various soil aggregate property which are helpful for the engineers, are nothing but its unconfined compressive strength, its permeability, and soil's void ratio, also the relative density or density index, activity number, which again is related for clay soils. So we have seen so much of these properties, which is soil aggregate properties, and we have also discussed the description of the soil based on its value. That means if you have the soil which has relative density or the density index of 0 to 15%, then we call it as a very loose sandy soil. And we have also seen particular definition related to clay type of soil depending on its activity number. And also we have quantified the soil is termed as inactive if it has activity number less than 0.75. So like this we have seen the description of the soil in quantitative scale. So similarly, onto the same basis, we have also seen the grain size distribution curve, in which we have seen how the particle size is actually varying with your repeat. In that we have seen how the particle size is repeat. In the grain size distribution curve, we have seen the particle sizes, how the soil in a particular soil, if it has got many particle sizes, then also we have seen how to classify the soil based on its size. That means we have seen that is particularly applicable for coarse-grained soil. That means we have for sands and gravel, this particular grain size distribution curve is much more helpful. But this we have seen it in the broader level. We have not gone it in the much deeper level. So we'll go into it in this session. So this session starts with the classification of the soil. So before going to the soil classification, we need to get an idea of the soil in general. So as you know, the soil that we found in nature has broadly been divided into two categories, like a clay soil and a sandy soil. So the soil which we say which is like a most behavior towards clay, we call it as clay, and the soil which has got a behavior similar to sand, that means high grain size, and it is contributed to a friction angle, it has a least cohesion, and it is again formed by a physical weathering. So like these are parameter which we categorize and we call it as a sandy soil, or soil which is most likely to behave as a sandy. But remember, this classification is just, we call it as, yes, it's sand, that means it has a friction angle, it has no cohesion, it is cohesionless. But vice versa for clay, we say that the cohesion is the most important parameter. The soil is also called as it is a fine grain. So like these are the parameter which, on the basis of which we categorize the soil, right? But in many of the cases, that means we have to establish the universal language to the engineers. So we just for mean the clay, it doesn't mean that it is a plastic in nature, or so suppose for sand, it is non-plastic in nature. So plasticity and all, based on those index properties, will classify a soil. So the history of soil classification is through the systems, which is first of all are introduced by United States engineers. So these systems are introduced by United States of the Engineers, and first man in the world is whose name is Coarse-grained, who has also developed a tool to determine a liquid limit. That also we have seen it in our previous classes. So Coarse-grained in 1948 has developed a system called as the Unified Soil Classification System. In short form, it is known as USCS, Unified Soil Classification System. Yes, because this all the research that he did is during World War II. During World War II, and it is came out in the year of hopefully the 1948. That means during an end of the World War II. So according to this unified soil classification system, it is introduced by the US engineers, has got a distinct characteristics. And these particular soil classification system is particularly meant for an highway construction or for an airfield construction pavements. It is particularly useful for construction of pavements, where the soil is used as a construction material. Airfield pavements and all, and also highway pavement, these classification are more useful. But we have again one more soil classification system, and it is named as AASHTO, meaning American Association of State Highway and Transport Officials. So there are broadly two categories, namely AASHTO, that is American Association of State Highway and Transport Officials, and Unified Soil Classification System, which in turn is developed by Coarse-grained. So the soil which is classified using a Coarse-grained approach or nothing but the Unified Soil Classification System is different from the AASHTO specifications. So we will go into deep in this particular chapter, and also we will discuss the Indian soil classification system. Indians have adopted the also called as Indian soil classification system, and we Indians have adopted the Unified Soil Classification System with minor modifications in it. With minor modifications, particularly in the plasticity chart, I call. So we'll go into deep in this Indian soil classification system, which is first of all universal, is Unified Soil Classification System, and we Indians have adopted the same Unified Soil Classification System with little or minor modifications in it. So we'll go and study this particular Unified Soil Classification System. But before going to discuss this Unified Soil Classification System, we will give you a quick review of the previously discussed chapters like grain size distribution curve, also called as GSD curve, in the index properties of soil. If you remember, in index properties we have two broad categories. One is soil grain property and another one is soil aggregate property. In soil grain property, we have seen its specific gravity, soil size, soil shape, or I specifically call grain size, grain shape, grain specific gravity, and grain mineralogical composition. So all these soil grain properties are not dependent on the history of the soil. Vice versa, for soil aggregate property, these property depend on the history or the formation of a soil. So in that we discussed this curve, grain size distribution curve, which gives us an idea of how the particles are present in the soil. So for this we have done a sieve analysis, and I told you we have sieves ranging from 300 mm or for 80 mm to 75 micron. So in that I've told you we have sieves ranging from an 80 mm, then we have 60, 40, 20, 10, but in between we have 12.5 mm as well. So we have ranges between starting from 80, and also we have 200, 300 above, for which are particularly used for boulders and cobbles. So like that we have many sieve sizes, and last sieve size that we have is 75 micron. So beyond 75 micron we didn't have a sieve set, we have just the pan. That's what we have discussed. And what we have also discussed how to get this grain size distribution curve from the sieve analysis test that we run it out in the lab. And we have seen, if you have sieve size, generally this sieve size has got a broader range starting from 80 mm to 75 micron. So therefore this has to be plotted on a log axis, and on the y-axis we plot generally a percentage finer. Percentage finer means 100 minus percentage cumulative that is retained on particular sieve. So we have also seen this terminology of percent finer. And if we have a particle size 0.001, 0.01, 0.1, and 1, 10, 100. So like that, if you have the sieve sizes, then percentage finer curve, or with respect to percentage finer, if I draw a curve, it looks like this. So it starts around 100, here it is 100, and here it is something like here it is 0%. It starts from this point, and gradually the curve will go and meet into a 0% line, and this particular curve we named it as a grain size distribution curve, that is GSD curve. And also we have seen particularly the cases, that is, if you have wide ranges of the particle size present in the soil, then it is called as non-uniformly graded, or particular we call it as well-graded soil. Well-graded soil meaning is that all the particles are present in your soil, and if you have only a range of a particle present is only in between suppose 10 to 0.1 mm, and probably we have a curve like this, and this particular soil we call it as uniformly graded, or the uniformly graded soil is also called as poorly graded soil. Remember, it's poorly graded. That means only a particle size ranging from 1 to 0.1 mm is present. So there is no particle size even greater than 1 or even less than 0.1 mm. So this is uniformly graded. And also we have seen skip graded soil. That means if you have a relatively flatter region in between, that which indicates that the particle sizes in between 0.1 to 0.01 are absent. So we have also seen this type of soil which is gap graded. So unified soil classification system has given ranges depending on the parameter when you call the soil it as well graded or non-uniformly graded, and when you call the soil it as uniformly graded. So this distinction between uniformly graded and non-uniformly graded is given by this unified soil classification system, and also they have given the soil classification based on the particle sizes, and this soil classification is as follows. Earlier also, first of all, we'll take the 75 micron sieve. 75 micron sieve is also called as US sieve number 200. Remember, 75 micron sieve is also called as US sieve number 200. So if you sieve your x kg of soil through this 75 micron sieve, what you will get if you have this 75 micron sieve, some particle you will collect it in the pan, while other particle will be retained in this 75 micron sieve, right? And some particle you will collect it in the pan. These are the particles collected in the pan. So what you will do, you will find out a ratio of the particles which is collected or retained by this 75 micron sieve. So if you have the particles which is collected or retained by 75 micron sieve is more than x by 2, remember, either you can do by this calculation by retained or by passing. So what I am doing is for the retained. If you have retained soil on 75 micron sieve, if it is more than x by 2, if this condition arrives, then we call the soil as coarse-grained soil. Then we call soil as coarse-grained soil. Same way, same definition, if you have the soil passing through 75 micron sieve, if it is less than x by 2, if the passing, that means the soil which is collected in the pan, which is a finer than 75 micron size, if it is less than 50% of the soil which you have taken it for sieving, then that condition also we call it as the soil which is coarse-grained soil. So remember, 75 sieve is very, very important in order to classify a soil into a coarse-grained soil or a fine-grained soil. So if you have the size more than 50% of a soil which is greater than 75 micron, then we call it as coarse-grained soil. If you have a soil which has a size less than 75 micron, or if you have a soil 50% or more than 50% of a soil which has a size less than 75 micron, then we call it as fine-grained soil. Here it is fine-grained, here it is coarse-grained. I'll write only short form CG and FG. 75 micron is, you need to do this first step initially, which is very, very important. Now if you have this condition satisfied, that means more than 50% is retained on 75 micron sieve, then you call the soil it as coarse-grained. Then once you're confirmed with this particular type of soil, that is you have coarse-grained soil, then you need to do the following steps. Then you need to take 4.75 mm sieve and you need to sieve it all the material which is retained on 75 micron sieve, So if you have again the retained material on 4.75 mm is greater than x by 2, that means if you have a percentage which is written on 4.75 mm is more than 50% of the soil, then we call this particular soil as gravelly. Else the soil is sandy. So that's how we'll classify a coarse-grained soil. So if you get this particular type of condition where you end up at getting gravelly or sandy soil, then we have that means if you have a coarse-grained soil, then you can use the GSD curve in order to further classify the soil into well graded and poorly graded. So this well graded and poorly graded soil you need to do by assessing two parameters. So these two parameters are very important. One out of this is the coefficient of uniformity, this coefficient is also called as C suffix small u, which is a ratio of D60 by D10. In our previous class also we have seen D10, it has effective size of particle. So from GSD curve you need to find it out the size of a soil which has got 60% of finer. So this is suppose 60% and suppose this is a 10%. You need to find it out this particular size. So you need to take this 60% and 10% ratio of the D60 by D10. You will find this coefficient of uniformity, and also the second parameter, which is coefficient of curvature, so called as CC. So as you go into this geotechnical chapter, you will again come with this particular notation CC in the consolidation chapter. So that's why you need to revise this subject as much as possible so that you will not get confused between those CC and those notations over there. So here it is coefficient of curvature, CC. So the CC is nothing but D square 30 divided by D60 into D10. So for coefficient of curvature, you need 30% finer. This is 30%. So the size corresponding to 30% of it. C size corresponding to 30% of the finer. So you need to take it. So these are the two important parameters based on which the soil can be either classified it as a well graded or poorly graded. So I have something to show in this regard. Is nothing but the table for the unified soil classification system. So you have this particular kind of a table. So see, if you concentrate on this table, here in this you have been given that if it is a coarse-grained soil meaning that more than half of the material is larger than 75 micron, that means 0.07 mm. So if you have more than 50% of a soil which is greater than this 75 micron, then we call it as a coarse-grained soil. If this condition is not satisfied, if this condition fails, then we call the soil it as fine-grained. So if the soil is you have called it as a coarse-grained soil, then it can be either sand or gravel. For classifying sand and gravel, you need to take 4.75 mm sieve, and if you have more than half of the coarse grain fraction smaller than this size, that means if you have the size which is in between 4.75 mm and 75 micron, if it is less than 50%, that means you have the sands. if you have a retained percentage on 75 microns, if it is greater than 50% of the coarse fraction, that means you need to deduct this fine grained soil or the finer fraction or the size of particle less than 75 micron, and you need to only consider the coarser fraction. If it is larger, retained percentage larger is greater than 50% on this particular sieve size, 4.75 mm, then you call it as a gravelly soil. So once you get to know about this gravelly and sandy soil, then you have got another again two classifications, which is GW and GP, and also GM and GC. So this classification of GW and GP depends upon the coefficient of uniformity and coefficient of curvature, that is Cu and Cc. So particularly for gravels, so if the Cu is greater than 4 and also as well as Cc lies in between 1 to 3, then we call it as a well graded gravel. If any of these two conditions fails, then we call it as a poorly graded gravel. So therefore I'll write it over here. For GW, that means for well graded gravel, gravel, you must satisfy this condition, that is Cu has to be greater than 4 and Cc has to be in between 1 to 3. This condition is must in order to satisfy this GW. But in this we have various terminologies called as GW, GP, GC. So I will give you what is this symbol, group symbol. So G here is prefix and this W it's suffix. So I'll give you this table of prefix and suffixes. So this prefix and suffix are only for the unified soil classification system. So for prefix, if you have G, it means gravel. If you have S, that means it's a sand. If you have C, that means it's a clay. If you have M, which means it's a silt. And in that also we have right, fine, we have O, means organic, and also we have P small t, that means peat. So peat and organic, these are nothing but the organic soil classifications. And if you have suffixes W, meaning that it is a well graded, and we have P, which is nothing but poorly graded. We have C, that means clay. Remember, this C is different, this C is different. C suffix, if it is a suffix, that means it's clay. M, that means it's silty. And yeah, L and H. L means if it has got a liquid limit less than 50%, and M means high liquid limit. High liquid limit means liquid limit greater than 50%. So these are the prefixes and suffixes in the unified soil classification system. G is for gravel, S is for sand, C is for clay, M is for silt, O is for organic, and PT is for peat, and W for well graded, P for poorly graded, C for clay, M is for silty, and L and H. L is when you have the liquid limit less than 50%, and H is when you have liquid limit greater than 50%. So in unified soil classification system, it is specifically said that if you have coarse grained soil, then you must run out the grain size distribution curve. So you must go into the sieve analysis particularly. But if you have got a fine grained soil, you must use this plasticity index or plasticity chart. So remember, for fine grained soils, the sieve analysis is not at all useful. Only for coarse grained soils, sieve analysis is useful as per this unified soil classification system. Since the Indians have copied or they have adopted this Indian soil classification system as it is, but with the modifications in it, so the same meaning has got continued for Indian soil classification system as well. So for Indian soil classification system as well, you need to use a grain size distribution curve for coarse grained and plasticity chart for the fine grained soils. But here we will see this plasticity chart, but before going to it, we must see this particular coarse grained soil, in that we are up to the well graded gravel and poorly graded gravel, and I gave you the definition of well graded. When both the condition has got satisfied for gravel, then we call it as well graded. Otherwise, even if any of this condition fails, then we call it as a poorly graded gravel. So remember, well graded gravel or poorly graded gravel is based on the assumption that you have got the percentage finer. That means if you read this statement, you need to find it out the percentage of the fines, that means finer smaller than number 200 sieve size. US number 200 sieve size, that means 75 micron size. That's what we have seen it in the previous slide. And also coarse grained soils are classified as follows. So if you have less than 5% of the soil which is passing through 75 micron, so if you have less than 5% finer fraction, then the soil is classified as either a well graded or poorly graded. So if you have a percentage finer more than 12%, here it is written it as more than 12%, then it is termed as gravels with fines, and these fines depends on the plasticity index. So if you have a soil which is particularly, I call it as GM or GC, called as silty gravel or clayey gravel, that means here gravel percentage is higher, silt is minor content. Same way GC, that means clayey gravel, which indicates clay percentage is small as compared to gravel percentage. So this distinction between a clayey gravel and silty gravel is based on the Atterberg limit, or it is based on the plasticity index. So as discussed earlier, similarly, if for well graded gravel as well as for poorly graded gravel, you must have the grain size distribution curve, and you go to this particular option if you have a percentage finer than 75 micron or less than 5%. So if you have more percentage finer, that means the particle size repeat. That means if you have particle size less than 75 micron and the percentage of it is greater than 12%, that means if your soil has got more than 12% of the finer fractions than 75 micron, then you may refer it to either a clayey gravel or a silty gravel. So in order to distinguish between the clayey gravel and silty gravel, you must know this plasticity chart and this particular A line, which is Arthur Coarse-grained line, and the equation of A line is given by this line is named after the scientist named as Arthur Coarse-grained. This equation of A line is 0.73 WL minus 20. This is equation of A line. Remember, this is very again important term, A line. So again you need to, if you have fines in the gravels exceeding 12%, then again you need to carry the test on the finer fraction, that means a liquid limit test and plastic limit test. So from liquid limit test you get the liquid limit, and from plastic limit test you get the plastic limit, and the liquid limit minus plastic limit you will get the plasticity index. And from this plasticity index and liquid limit you need to plot it on this curve, and if the point is above A line then you call it as a clay, and if the point falls below A line then you call it as the silt or organic soil. And also if you read over here, which is given clearly that if the Atterberg limit is above A line, then this particular is for a clay gravel, and if it is below A line, then it is for silty type of sand or silty type of a gravel. But if the liquid limit is particularly in between 4 to 7, here it is a 4% and here it is a 7%. So if it is a 4 to 7%, then you need to give a dual symbol. That's what it is mean by a dual symbol. Dual symbol means it is a GC and GM. So if you have, if the point or if the plasticity index is in between 4 to 7%, then you need to give dual symbol like GC and GM. So that means clay gravel as well as silty gravel. So that's what it means by the dual symbol. And correspondingly, if you got a percentage finer than 75 micron lies in between the 5 to 12%. So here also, if you read, borderline cases require to give a dual symbol. So here dual symbol means either well graded clay gravel or poorly graded clay gravel, or poorly graded silty gravel or poorly graded clay gravel. So like that we have to give symbols. So I will summarize this classification of if you have, when you will go for coarse grain, it is pre-understood that more than 50% of a soil is retaining on 75 micron sieve. So if this condition is true, if this condition holds good, then you call it as the soil is coarse grained. So once you get to know the soil is coarse grained, then you need to sieve it through 4.75 mm sieve. So write it over here, 4.75 mm. So if more than this coarse grained fraction is retaining on more than 50% of the coarse grained fraction is retaining on 4.75 mm sieve, that means it is a gravel. And if the more than 50% of a soil is passing through 4.75 mm sieve, then it is a sand. So this is the border or boundary between a sand and a gravel. So once you get to know the soil is either gravel or sand, you need to again use the percentage finer than 75 micron. That means percentage of clay plus silt, or I will call it as percentage of fine grained soil. So if this percentage, I will call it as X. So if X is less than 5%, then you will give the symbol for a soil like well graded gravel or either a poorly graded gravel. So well graded gravel and poorly graded gravel is particularly based on this X percentage, that means percentage of this fine grained soil. So if this X is greater than 12%, then you'll classify a soil into two groups like clay gravel or silty gravel. Clay gravel when it plots above a line, and if it silty, that means it plot below a line. And again, if you have a border, that means if the x lies in between 5 to 12%, then you need to use a dual symbol, like it can have four symbols. First, it can have well graded gravel with coupled with clay. Again, you need to have this particular plasticity chart, and from that you need to do a liquid limit test and plastic limit test. For well graded gravel along with the silty gravel. C and D is for poorly graded gravel, clay gravel, and poorly graded gravel, silty gravel. So these are the dual symbols which you need to incorporate when you have percentage of fine grain in between 5 to 12%. Remember, this is important. So we have seen when you go for well graded gravel, if and only if this two condition is satisfied, that means if Cu greater than 4 and the Cc in between, if both the condition are satisfied, then you go for well graded gravel. If any of this condition fails, you call it as poorly graded gravel, GP. You go for a GP if any one of these two fails. Then we have just now seen a sub-classification for gravel. So on the same basis, for sand, you have got, for sand, I'll write 4.75 mm. I got this sandy soil. For sand, we have again X percentage, that means percentage of fine-grained soil. Percentage of fine grain, I call it as X standard, not a standard, just for making things simple. So if you have X, that is percentage of fine grain less than 5%. So if it is less than 5%, we go for well graded sand or poorly graded sand. So well graded sand and poorly graded sand. When we call it as well graded sand, when both the conditions satisfied, that means Cu, here it's a change, greater than 6, rest of the thing is as it is, and Cc in between 1, 2, 3. For gravel we have 4. For gravel we have Cu greater than 4, Cc in between 1 to 3. But for sand, just small change. For sand it is Cu greater than 6 and Cc in between 1 to 3. Then and then only if all the two conditions are satisfied, then we go for well graded, else we go for poorly graded sand. And similarly, this sub-classification is same. If you got X greater than 12%, then you need to do plastic limit test, liquid limit test. Based on that, we have clay sand and silty sand if it plots above a line and this plots below a line. Continuation to soil classification. So if it plots above a line, then it's a clay. If it plots below a line, then it is a silty. So same way here, from this table, if it is plotting above, it's clay, and if it's plotting below, that means it's a silt. And also we have got if the X, that is percentage fine grained soil, is in between 5 to 12. So we have got again the 4 subclasses A, B, C and D, which gives a dual symbol to it. Dual symbol means well graded sand with silty sand, well graded sand with clayey sand, poorly graded sand with clayey sand, and poorly graded sand with silty sand. So that's how we'll give the name. Remember, clay sand. So when I will name it as clay sand, clay sand, which indicates that clay percentage is less than sand percentage. This is very important. So you have silty sand, that means silt percentage less than sand percentage. And remember one more thing, which is very important. For only sand you have got this number 6 for SEU, except this 6 everything is same. And absolutely the lower bound limit for sand is 75 micron, that means 0.05 mm. So sand has to be in the range of 75 micron to 4.75 mm. And even if it is below this, then we call it as fine grained soil, and it's clearly understood. And but if this soil is fine grained, that means more than 50% of the soil is passing through this 75 micron sieve or US sieve size number 200, then you need to use this particular chart, which is called as a plasticity chart, and this is for laboratory classification of fine grained soil. If you remember over here, if it is got silt and clays, and also liquid limit less than 50%, liquid limit greater than 50%. So based on the laboratory classification, you will find it out dry strength, dilatancy, and toughness. Remember, all this exercise is done it in the lab. I'll tell you first of all this dilatancy test. For this test, what you need to do, you need to have a lump of a soil which is fine grained soil, and you need to just add some water in it, and you need to squeeze it between the palms. So when you just squeeze it and you just press and then you remove the load, and you'll see the rate of dissipation of the water. So if you squeeze it, water will be moved out of its volume, and quickly it is again absorbing that water which is moved out. So that reaction we name it as quick. So if the water is slowly absorbed by the soil, then we call it as slow. And depending on this particular quick to slow, none means if you just press it and just you remove it, then the water will be there around it, but no water or very little amount of water is getting absorbed by the soil. It gives an identification of none. So if it is none, then it is a CL. CL means low liquid limit with the clays. So that's what it is given. If the liquid limit is less than 50, it is suffix given by L, and if it is got more than 50%, it is given by H. So this L and H is nothing but, you can call it as low compressible or even high compressible, because if it has got more liquid limit, then absolutely the reduction in the volume once you apply a load is very high if the liquid limit is very high. So the compressibility, which means volume change, is directly proportional to liquid limit. So therefore, for higher liquid limit, if you go, then we have the higher chances of compressing the soil, or higher will be the change in the volume from liquid limit to its dry state. So also with this reference to the toughness is nothing but the shear strength of a soil at plastic limit. So this is also determined in the lab just by molding and remolding a soil and near to the plastic limit, and you just need to have, just need to apply a load by your hand, and you just need to find it out how the tough is based on this medium, and you need to classify the soil based on the same categories. In this also you have to use this kind of a chart, which is for plasticity chart, which is meant purely for a fine-grained soil. So here is limit, which is nothing but 50%. So if it is more than 50, the identification is either the CH or the OH. OH, that means it is organic, highly compressible organic soil, and if it is less than 50%, it is OL or a CL. OL, that means it is a low compressible organic soil or a low compressible clays, and if it is even here it is a 35%, then it is a ML, that means low compressible silt. So relatively this O and M takes over same meaning. If it has got an organic fraction, then it is M, then it is a O. But if it is, but the soil, the fine-grained soil, if it has got a non-organic fraction, then it is M. So if it is below A line, either it is a organic or it is a silt. So this organic and the silt is depending on, or depending by the terms, which is nothing but the color, odor, spongy feel, or the fibrous texture. So if it has got a zero odor or zero spongy filling, so this is particularly a lab test which you run it out on the fine-grained soils. So if you didn't smell, or didn't you smell bad or vigorous smell, then you particularly notice it might be a silt if it plots below A line. But if it is plotting above A line, then it is a clay. And also, if you have got this particular region which is shaded in this diagram, then you need to give it the dual symbol CL and ML. This particular lower limit is for 4% plasticity index, and a particular upper limit of plasticity index equal to 7%. And this all above whole range is for low compressible clay soils. And if you compare the two soils, and that's what we have highlighted while discussing the toughness index. So what is the toughness index? We have discussed about this particular point, that the toughness index is nothing but the ratio of plasticity index to the flow index. So if you compare the two different soils at same plasticity index, that's what it is highlighted over here. If you compare comparing two soils at equal liquid limit, the toughness and dry strength increases with increase in the plasticity index. So the toughness and dry strength are directly proportional to the plasticity index. So if you increase plasticity index, the toughness of a soil is absolutely going to increase. So this finishes your first classification system, which is nothing but Unified Soil Classification System, USCS. We'll move ahead with the AASHTO soil classification system. So AASHTO, that means the American Association of State Highways and Transport Officials. State highway and transport officials. So based on this AASHTO classification, they have grouped the soil into 8 different categories. So these categories will start it at A1, A2, A3, and will end it at A7, and the different group, that is 8, is meant for organic or peat soils. This is a different class of a group, that is A8 group. So this A1 group A2 group, A3 group and A7 group are depending on a particular index, and that index is called it as a group index, or also we call it as GI, group index. So the definition of group index is as follows. So group index gives the idea about the strength of a soil. The group index at what we are discussing is nothing but the which is measure of shear strength of a soil. So group index is given by mathematical formula 0.2 A into plus 0.2 into A plus 0.005 A into C plus 0.01 B into D. So based on this group index and all these parameters A, B, C and D, the soil is classified into 8 different categories starting from A1 up to A8. But remember, for the last category A8, this particularly is useful for the organic soil. So what is this all terms? I'll rewrite the definition of group index of a soil, which is 0.2 A plus 0.005 AC plus 0.01 B into D. So this is how the definition of group index of a soil is. So what is this term A, B, C and D? So this term A depends upon the percentage finer than 75 micron. That means percentage of fine grained soil in the given soil. That means the size of a particle less than 75 micron. So how much percentage of fine grained soil is present in your given amount of a soil? So particularly follow the last class, we have marked this as a X, percentage finer than 75 micron, minus 35 is the A. Similarly for B, it is X, that is percentage finer than 75 micron, minus 15, and C is liquid limit in excess of 40%. This is 40%. Remember, everything X and all is in the percentage. Liquid limit, you need to put it in the percentage value, and for D it is a plasticity index in excess of 10%. So the limits for all these A, B, C and D are as follows. For A, the limits are from 0 to 40. For B, limits are again same, 0 to 40. For C also limits are 0 to 40. For D, the limits are from 0 to 20. For C as well, the limits are from 0 to 20, not 40, from 0 to 20. Limits, these are the limits values. So if you have got a percentage, let's suppose it's 30% of the soil is finer than 75 micron, then probably you will end up at getting this value of A, which is negative. That means 30 minus 35, which is minus 5. So if you get any of this A value, any of this value A, B, C or D, if any value is negative, then you need to replace it by a number 0. Then replace it by number 0. You need to put it 0 value, and if you have got a percentage finer equal to, let's suppose 80%, then 80 minus 35 will become equal to 45. So again it has gone beyond the 40, so therefore you need to restrict it to the 40. So that what is the meaning of these limits is. So for all these A, B, C, D, the limits are 0 to 40. For A, B, limits are 0 to 40, and for C and D, limits are between 0 to 20. Remember, and everything you need to put it in the percentage. So by evaluating GI, group index, you will be classifying a soil into all that 8 group that what we have discussed in the previous slide, that is from A1, A2, A3 up to A8. So the group index of a soil for most of the soil lies in the range of 0 to 20, and it is a number and which is a dimensional list, so it doesn't have any kind of unit. But the group index equal to 0 indicates it has got good strength, good, or it may be considered as good as a construction material, and group index equal to 40 has got poor strength, or you may call it as not suitable for the construction, not suitable for construction purpose. So based on this group index and all these values, percentage finer and liquid limit and plasticity index, we classify the soil as given in this table. So it is the AASHTO soil classification system, where here there is a general classification starting from A1 and A3, A1, A2, A3, so A4, A5, A6 and A7. So group number A1 has, when we call it as group number A1 when all this condition has got satisfied, all the condition listed over here. So first of all, percentage passing, it has to be maximum restricted to 50, maximum 30, maximum 15. So similarly for all these classes we got a number of constraints, and based on these number of constraints we will classify a soil based on the group index as well as liquid limit, plasticity index, and based on your sieve size, that is how much size the particle is passing or retained, something like that. So as we have discussed, we have 7 groups, and A8 is for peat, or you may call it as for highly organic soils. So if you go to the A7 group, then it has got a maximum limit of 20 group index, which means that the soil is clay soil, and for general rating as a subgrade is fair to poor. So you cannot use the soil as subgrade, but vice versa, if you have got good group index close to even a 4 or less than 4, then it is sand, stone fragment, gravel, and that's what is the description of the soil, and it is considered as in between excellent to good. So you must have, as in being engineer, the group index value near less than 4. Okay. So by this AASHTO, that is American Association of State Highways and Transport Official, has given this smart chart in order to classify a soil into all these groups. So this finishes your AASHTO soil classification system. Thank you.